So this is the Relu module, which is the smallest module among the entire program. So this is quite simple and straightforward. What was your input? 4W. What was your output with 2W? So we have seen that activation function was a reason your truncation was happening and you were getting 2W instead of 4W. What is the reason behind this truncation? I don't want to store and eat up my memory by storing 4W outputs for every layer. What if my layer number of neurons in my layer were 196 or 200? So imagine storing 4W for each neuron. Quite impractical and quite a wastage of memory. If you're getting an important information from the truncated output also, why not move on with the truncated value? So this sort of truncation has to be done using hit and trial method. You just see how many bits can be truncated, and still if you're getting a good enough output, this means your code works well and you can proceed. Especially for a program for a problem like MNIST dataset classification, it's quite feasible to go on with 2W because it's a simple prediction and you can easily move on with this sort of truncation. So why am I going with Relu? The first thing before proceeding with this program in Verilog is you have to try this out in a Jupyter notebook. In Jupyter notebook or a Google Colab, we have to first go through, we have to first compute, like build a neural network using your TensorFlow or using your scikit-learn, and then you have to do the predictions. You have to play with the parameters, play with your activation functions, and find out which activation function is giving you the best prediction. And one more thing I want to mark here is I want to mention here is the weight and the bias array which I was obtaining was from a Python script. I had first done this code in Python. I have first done this neural network thing in Python, and I've built a neural network there. I have done the dataset classification there, and after that, after the training was completed in Python, I have obtained that weights and biases that I'm using, that optimized weights and biases I am using as it is in this Verilog module. This means no backpropagation was being done in Verilog. So basically whatever weights and biases I have obtained from my Python script after training in Python, I have done the training in Python. Whatever weights and biases I am obtaining after optimized weights and biases I am obtaining after achieving a good accuracy from the Python script, I'm using it as it is in my Verilog module. Backpropagation is not implemented in this Verilog code. Okay, that is one important point to be noted. Other thing is this decision of choosing Relu module is also on because in Python script I have done this hyperparameter tuning and found out that Relu works better than Sigmoid for my case. Okay, so that's why we moved on with Relu instead of Sigmoid. Now, so what are the pros and cons of Relu? One of the pros is your negative outputs will act as a dead neuron because Relu graph, if you see, for less than 0, it is 0, but for more than 0, it is the input is equal to output. If it is if the input is positive, input is equal to output. Okay, it's a linear graph for positive values. So what happens in sigmoid, if you see the sigmoid graph, it is an S-shaped graph. So in S-shaped graph, what happens? For values, for higher values, it saturates. It is a straight line. And similarly for lower, extremely lower values, it also saturates. So when the saturation happens, it results in a problem of vanishing gradients. Just have a look at vanishing gradients from any YouTube video, or maybe if possible I will make a small intro on vanishing gradients so that we understand this Relu quite better. So Sigmoid has this problem of vanishing gradients, that's why Relu works best for my case. So this is more of an hit and trial method that we have done in the Python script, and then we came with the decision that Relu is the good activation function to go with. Okay, so this is quite a simple logic. That is, if data in is positive or greater than 0, my output will be data in because it is a positive. And if it is negative, my output will be 0. I am truncating here from 4W to 2W. Your 4W means 4 into 8, 32 bits I had. I'm right shifting it by 16 bits. So I'll obtain 2W, that is 16 bits. If I'm truncating by 16 bits, I'll obtain a 16 bits output. So this is basically truncation I'm doing here to obtain the 2W data out. So let's discuss the concept of vanishing gradients here. So very briefly, we'll discuss this vanishing gradients concept. So let's say you have a small neural network like this. So every previous layer is connected via weight, and this is my output. Okay. So see, first randomly your weights will be initialized. What happens in the training process? Randomly your weights will be initialized and randomly an output will be computed. Now that output is being compared with your uh, golden value. Golden value means the predicted output is being compared with the original output, and you compute the loss. And when you see that the loss is more, you back propagate and then you optimize the weights and biases to obtain a good prediction. This is the basic gist of what is happening in back propagation. So, uh, what is the equation if, let's say, this is YW and this is WX? Let's say I have achieved a very big loss. This means my neural network is behaving in a very unoptimized manner. So I need to change my weights. I need to tweak my weights and biases a little bit to obtain a good prediction. So what is the equation for that? WX is equal to WX minus learning rate, which is denoted by alpha, into the gradient. What is gradient here? Gradient is the derivative of loss with respect to derivative of Wx. That is your weight. How much your loss have changed with respect to the weight. Okay. So this is basically a very small value, and alpha is also somewhere around 0.1 to 0.001. Okay, so this is also very small value, and this gradient is also very small value. For a sigmoid, the gradient is somewhere between 0 to 0.25, which is a very small value. When you multiply the small value, this is a very small value learning rate, and this gradient is also a very small value. When you multiply these small values, you get even more smaller value. So your Wx is equal to Wx minus very small value. So what happens? Wx is practically not changing. You did not change your Wx a lot. Similarly, if you see the Wy equation, it is somewhat like this: Wy minus learning rate into the gradient. The gradient is a chain rule because this is the first layer. This will be the loss upon the Wx into derivative of Wx by Wy. So this chain rule is applied here. So these all derivatives are small value if you apply a sigmoid activation function, and this derivative basically tells you how much your loss is changing with respect to your weights, and that is, if that is a very small value and your learning rate is also a very small value, then multiplication will give you an even more smaller value, and practically your weights are not changing. What this subtracting something very small from this means this is practically same. So if your weights are same and the loss is not, the back propagation is not making a serious effect, or it is not basically changing your weights to your optimized weights, your weights are not updating properly, neural network will not undergo a good training, and neural network will never learn, your neural network will never learn good patterns, which is a very bad thing. So this vanishing gradient problems arises in case of sigmoid. So Relu is a good option in case of in order to avoid this problem, because the derivative is somewhere between 0 to 1, so it is a little larger value than that of the sigmoid. So that is why Relu works better in case of vanishing gradients problem.